One great use of implicit differentiation is being able to take the derivative of the inverse trigonometric functions. For example, if the function is the arc cosine of x, then what we could do is write this as a cosine statement, cosine of y equals x, and then use implicit differentiation to find y prime, or in other words, the derivative of arc cosine of x. So we can do that by taking the derivative with respect to x of both sides, remembering that y is a function of x, we have to use the chain rule there. So the derivative of cosine is sine of y, negative sine of y, times the derivative of y, which is y prime, equals the derivative of x, which is 1. So y prime is negative 1 over the sine of y after we divide both sides by the sine of y. That's the same thing as negative cosecant of y. Now, we would like to have this in terms of x, right? Just like y is in terms of x. So what we can do is use this statement up here to learn about y, the relationship between y and x. Well, the cosine of the angle y, so I'll sort of draw a right triangle here, name one of the angles y, the cosine of that angle is x. So the adjacent over the hypotenuse has to equal x, or x over 1. So we will just say that x is the adjacent and 1 is the hypotenuse, which means the opposite side would be the square root of 1 minus x squared. So now we've learned about the angle y, which is what we're dealing with down here. And in particular, I want to know the cosecant of y, right? So the cosecant of y would be the hypotenuse, 1, over the opposite, square root of 1 minus x squared. Now I can come back and say that my derivative of arc cosine, my y prime for arc cosine, is negative cosecant of y, which is 1 over the square root of 1 minus x squared. And there we have the derivative for arc cosine. Let's do this again for the arc secant function. We're trying to find the derivative. So I first rewrite this as a secant statement. The secant of y is x, which we could translate even further if we like into a cosine statement, but we can do this. Let's go ahead and take the derivative of both sides with respect to x. In other words, do our implicit differentiation. The derivative of secant is secant times tangent, but then I've got to take the derivative of y as well, so that's times y prime, and the right side is 1. So dividing, I see that y prime is 1 over secant of y times tangent of y. Now I would like to be able to write secant of y and tangent of y in terms of x. So I need to do that by coming back up here to this statement. Secant of the angle y is x. Well, so that's this guy right here already. So I could go ahead in my next step down here and say y prime equals 1 over x times the tangent of y, which I still have to determine up here. Okay, so if secant of y is x is x over 1, and secant is hypotenuse over adjacent. So my hypotenuse is x, my adjacent side is 1. My opposite side then would be the square root of x squared minus 1. And now I can see that the tangent of y, which is what I want to know about down here, the tangent of y would be opposite over adjacent, which is the square root of x squared minus 1, divided by 1. So I just get the square root, and that is the tangent of y, and I'll put that here. So this is the derivative of arc secant. And you could proceed to do this with all of the inverse trigonometric functions.